Thank you very much, Chairman, for the introduction, and also I thank the organizers for putting this wonderful workshop together. And I'm also from Sungkyunkwan University. As a previous speaker, although I'll be talking a little bit different. And I'm sorry I have to leave tomorrow, so I think my session is on Thursday or something like that, so I was shifted here. But hopefully I will entertain you a little bit with this new concept of chiral phonons. So you might have heard about this chiral phonons, which is rather a new concept. I myself didn't know about this 5 years ago. And I'm working on mostly about oxide superlattices. And today I will show you that in this strontium ruthenate-based superlattices, you can propose that this chiral phonon mediates this exotic exchange interaction, interlayer exchange interaction. So this is the transmission electron microscope image of one of our samples. Basically, this is not a superlattice. So the bright layers are the strontium ruthenate layer, and these dark layers are strontium titanic layers. So basically, you control the thickness of the strontium ruthenate from 2, 4, 6, 8 unit cells, where the 1 unit cell of this layer is 0.4 nanometers. So you have very good control of this system using pulse laser epitaxy. So this work was primarily done by my former student, Sungkyunkwan, who is now a postdoc in our group for now. But he did most of the work. He went to Germany, he went to US to measure different aspects of his own samples. So he made all the superlattice samples. And here are some of the publications. And today I will talk mostly about this Science Advance paper that came out earlier this year. So this is the guy who did the work. So this is the contents of my talk. So I will start introducing you about the concept of chiral phonon. What are they, and what aspect do they have? And I will talk a little bit about the system, because I'm basically a film grower. And then I will talk 3 different aspects of this. First, magnetization, apparently, and then the spiral spin state, atomical resolution of this spiral spin state, and then about this chiral phonon and Zeeman effect. Then I will summarize. So these are some basic ideas on, I should say, transverse waves, right? So you have just 2 different waves with 2 different polarizations, I should say. So you can have vertical polarization and horizontal polarization. And this is well established in photon, I should say. So you have a photon is considered as a transverse wave, although this is quantized transverse wave. You can have orthogonal polarizations, and they can be superposed. And if you have no phase difference, they are still linear polarization, but with some phase difference between these 2 waves, you can create this circular polarization, or chiral, introduce chirality to this system. And this is why you have a spin-1 system for your photons. They are spin-1 bosons. They don't have any longitudinal modes. That's why they don't have spin-0. But basically, this is how you can make the photons interact with the magnetic field or magnetic moment. It turns out that phonons are not very different. Of course, they have mass, so that they are different. But you can, in 3-dimensional space, you have 2 different polarization. They are orthogonal. And if you have 2 different polarization, then you can actually introduce a phase difference between the 2. And this transverse acoustic or transverse optical mode can become a superposition with a phase difference. Then you can actually visualize this rotation motion of this polarization, of this ionic motion, actually. And this is actually called as chiral phonon. So basically, construction of this chiral phonon is not difficult. It's very easy, actually. So if you have just transverse waves, then you can make chirality to it in 3D space. But the question now is, if you have something like that, will it interact with the magnetic field, or will it create a magnetic moment inside the solid? Okay, So that is the questions that we are having, and people have been looking into it. So this is one example. This is actually a theory work back in 2014. So what this paper says is angular momentum of phonons and the Einstein-de Haas effect. So basically, Einstein-de Haas effect is the connection between the angular momentum and the magnetic moment in macroscopic scale, right? So, and this microscopic object of phonon, if they have the chirality or angular momentum in this, in their term, this angular momentum can effectively create this magnetic behavior, magnetic-like behavior, right? So this is the basically you just write the microscopic picture of your angular momentum of phonons. This is the displacement, and you have velocity vector, and you get the angular momentum, right? So, and they do show, at least theoretically, they can have some Einstein-de Haas effect. So again, emergence of this microscopic phonon chirality to the larger scale macroscopic angular momentum. More recently, Spalding proposed this orbital magnetic moments of phonons. So I hope this is also not very difficult. So if you assume a ionic motion, so this is for the ionic crystals. If the ionic motions have the circular motion, because they have charge, the circular motion will create this magnetic moment. Okay, so depending on the anion and cation, you have different magnetic moment. But basically, if you have a circularly polarized phonon, the circularly polarized phonons can carry orbital magnetic moments, and then this will interact with other magnetic moments or fields. Okay, so so people are more discussing about this new type of phonons, new polarization phonons, and try to link this with the magnetic behavior of the materials. So actually it turns out there are many different studies. So these are some of the studies that we could find in the references. There are lots of different phenomena and lots of different systems. And there are some of oxide systems and also in 2D materials. So what I feel is that there isn't any particular criteria of having this chiral phonon. So they are more universal in 3D or even in 2D lattices, and but you didn't look for it in the past. So now people are more interested in this. So in our group, in this talk actually, we are looking into strontium ruthenate, strontium titanium superlattice, which I have shown you in the first slide of the electron microscope image, and I'll be talking about this static. So most of these were dynamic observation of this phonon. But this talk will focus on the static interlayer exchange interaction. All right, so what we are going to talk about is something like this, I think. These arrows should be here, basically. So we have this system. So ferromagnetic metallic layer and non-magnetic insulating layer. So this non-magnetic insulating layer is sandwiched by this ferromagnetic layer. And we want to see any crosstalk between this ferromagnetic layer. So depending on this thickness of this non-magnetic insulating layer, the spin orientation between the up and down layer, upper and lower layer, will change. Okay, so that's the key idea. And we propose that this chiral phonon inside this non-magnetic insulating layer will convey the information of the spins from one layer to the other. Okay, so to do that, we need high-quality synthetic heterostructures, and that's why we turn into these oxide systems. So we have been working on this strontium ruthenate, strontium titanate system for a while now, and we have been able to propose different ideas like dimensional crossover and this phase instability within this dimensional crossover. Or we looked into the structure of this microscopic structure of this system, where this octahedral tilt pattern can be transferred, or it can be tunneled through this insulating layer. But anyway, so if you're interested more, you can talk to me later, or we can discuss it later. But basically, we have very good superlattices. So this was the first image that I showed you. And this is more larger scale, focused image. And this was done by, this TM was done by Professor Young-Min Kim in our university. So you can see that 6 layers of strontium rusinate separated by, in this case, 6 layers of strontium titanate. This is 4 unicell and this is 2 unicell. And you can see slight intermixing, I should say, of this rusinate layer because probably of this step structure of the substrate. But basically, you have very good high-quality superlattices grown by polarized epitaxy. So this also signifies the superlattice structure. So previously, this was not a superlattice. This was a heterostructure that we made to present the high quality, but this is actually superlattice structures. And you can see this beautiful, superlattice peaks appearing all over, as expected. Okay, and we can also work on this phonon dispersion modulation. If you have this nice superlattices, so you can create zone-folded acoustic phonon, and you can engineer this phonon wavelength. And for example, you have this zone folding for your superlattice systems. You can have additional peaks appearing for your phonon, and this is called as a zone folded acoustic phonons. And here you can see with different types of superlattices, you can actually see from Raman spectroscopy this evolution of this phonon peak depending on the superstructures, even for the oxide systems. Okay, so now we look into the magnetic behavior of the superlattice. So this is conventional magnetic behavior of the I should say, ferromagnetic layer. So strontium rusinate is a ferromagnet, 113. So you have a TC of 150 Kelvin or something like that. And you can see the increase of the magnetization. And you can see also the magnetic hysteresis loop as expected for the strontium rusinate. But now if you make a superlattice, so in this case, this is 6 unicell layers of SRO. This is 4 unicell layers of STO. So you separate your SRO layers with these STO layers and repeat it for 10 times, then you can see some clipping of this hysteresis loop. Okay? So at high temperature, you have just single loop, but at lower temperature, you start to see this double loop-like behavior. So this caught to my eyes and to the experiment. And also you can see similar temperature where this clipping starts, you can see drop of this magnetization. So there's some kind of antiferromagnetic-like behavior at this low temperature, and this was the curiosity. And furthermore, if you look into the STO thickness dependence, so you fix the SRO thickness and change the SRO, you fix the SRO thickness and change the STO thickness, so you change the separation between the layers, then you see some kind of oscillation-like behavior. So if you follow this lowest temperature magnetization, this is 6.2, 6.4 goes up, 6.6 goes down, but 6.8 goes up again. So this was kind of puzzle to us at the first time. So first time if you see something like this data, you see something is wrong. So either this experiment is wrong or the sample is wrong. So there can be many things that can go wrong. But this is the data. But Sungkyunkwan was quite persistent to do the same experiment for different sets. So now you have the second set. You see more or less the same, at least qualitative behavior of this oscillation. And it turns out he made more than 350 samples, superlattice samples, and he made more than 40 in-plane measurement. And you see this type of oscillation everywhere. Okay? So as a function of, again, if you look into this, you fix the strontium rusinate layer. Previously, this was the sample. And you change the STO thickness layer, then you see this oscillation. But if you go for 8 unicell of SRO, you still see this oscillation. 4 unicell of SRO, you still see this oscillation. So if something like this comes up, then you have to believe this type of oscillation is real. Okay? So at low temperature, you have some magnetic ground state that oscillates with the thickness of the interspacing layer. Okay? Okay, so what's going on? Okay, So there was the question. So we can approach something like this. So we start with now changing the number of layers. So here you have two Structurewith layer. The repetition is only 2. Now you have very suppressed magnetization, meaning that something like this might be happening. So you have the opposite direction of antiferromagnetic. This is, by the way, called synthetic antiferromagnetic ground state. On the other hand, if you have third layer, one more layer, then you have a boost of this magnetization, and you can expect something like this. And 4, you should again expect something dropping, but if you go for fifth layer, it doesn't match anymore, so it should go up again, but it doesn't go up as much as you expected, so it doesn't work. But now, if you rotate this a little bit and make the vector sum of this magnetization, and then you can have something like this situation, then you can, to some extent, account for this type of magnetization. So that was our idea. Of course, we need some reference layer. Probably that's where the symmetry breaks at the interface between the substrate or the surface. But basically, you can at least explain this type of experimental data. Okay? So you can do all sorts of things. You can just add, again, this factorial sum of these different layers, and then you can, to some extent, match this type of Z dependence. So this, again, repetition number dependence, and also the Y dependence, which is the STO thickness dependence. So, and based on this, we were to some extent trying to see how this kind of rotation, in this case this is 160 degrees rotation from one layer to the other Structurewith layer, and then we wanted to actually see this. And to do that, we have a tool that actually gives you, this is the polarized neutron reflectivity data done in spallation neutron source in Oak Ridge National Lab. And here you have polarization of your neutron for up and down neutrons, and you can write this. This is based on simulation, actually, but what you see is the best fit results from this type of 160-degree rotation of your spins, depending on the layer number of our superlattices. So we have 2 different experiments that corresponds to the same magnetic ground state in our superlattices. Okay, so what's the possible origin? So we first looked into the RKKY interaction because, well, there are many different origins actually that can explain the magnetic interaction between the heterostructures, super exchange, dipole-dipole interaction to start with, orange peel model, and but there aren't any that discusses the spacer layer thickness dependence, okay, except for the RKKY, of course. So RKKY actually gives you the oscillation. So there are cosine term and sine term in this, and there are oscillation of the J value, which is the exchange coupling or exchange integral, and it changes sign as you have the thickness between these 2 localized spins. But for the RKKY interaction to work with, you need an itinerant electrons, and your spacer layer should be metallic, and which is not the case here. The STO layer, actually, you can measure this junction transport, and SRO system is, of course, again, metallic, but you can see this huge resistivity increase, which is the resistivity value is that of the wood, actually, and you can see that this is actually the insulating, coming from the insulating behavior of the STO. So across this insulating layer, RKKY interaction cannot work well, okay? And so that's why we think there are chiral phonons actually mediating this. One indirect evidence is that you have a wavelength of this phonon coming from the phonon velocity of SRO as 5,000, which is about 3 nanometers. And this is roughly in the order of the rotation period that we observe in this oscillation of the magnetization. Unfortunately, we don't have any microscopic picture for this type of chiral phonon-mediated exchange interaction. Actually, this is a very new idea that has not been proposed in anywhere. So we hope that there can be some theory working with this. We have but other evidence that can discuss this origin as the chiral phonon. So if you look back into the phonon modes of this strontium ruthenate, there are two different phonon modes. One is called AG5, the other is B2G4. And they have the phonon wavelengths of 350 and 391 wave number. Okay? But they are in bulk orthorhombic lattice, and if you have this in tetragonal structure within the superlattices, they should become degenerate. So basically these two are the same modes. One is oscillating left and right, the other is oscillating up and down. So they both can be pardon? 10 minutes? Okay, so they are orthogonal polarization modes. And if you introduce somehow a phase difference between these two, you can actually create this type of chiral phonon that I have introduced in the first slides. Okay, so if you look just this behavior, then you would see only one phonon again, because this is calculated for the orthorhombic lattice. If you have tetragonal lattice, this should have the same wave number. And that's what we see at higher temperature. So this is the confocal Raman spectroscopy data that we took for our superlattice samples. By the way, oxide thin films are very difficult, very challenging to measure the Raman spectroscopy, and this was only possible because of the confocal tool that we could have access in Germany. So at high temperature, you only see only one peak that's coming again from this both of this polarization. But as you go lower in temperature, and you can see 10 Kelvin or 50 Kelvin data, you can actually see that there are two peaks. And if you look this behavior, you more or less see the splitting of this peak at about 130 Kelvin. So what we think is this is the reminiscence of phonon Zeeman effect, because there isn't any structural transition across this ferromagnetic transition temperature. So there's only magnetic ordering below 130 Kelvin, and there's no way that this phonons can be separated by this. But what you actually see is that below 130 Kelvin, there is a ferromagnetic ordering, and there's an internal molecular field that actually acts as a magnetic field applied to these phonons. Okay? And if a magnetic field is applied, and you can actually see that these type of chiral phonons can emerge, and depending on the polarization, they can have energy, additional energy or lesser energy from their original state. Okay? So that's what we think, that we have actually observed this phonon Zeeman effect in our samples, and that corroborates with the existence of chiral phonon, and that can make this magnetic oscillation and magnetic interlayer exchange interaction in our samples. Okay? So this is a summary. So we think this is the manifestation of the chiral phonons in our synthetic system. So this is the first static manifestation of the chiral phonons. And this chiral phonon acting as the unconventional interlayer exchange interaction. And realization of this novel system, synthetic system, can become a playground for many different topics in physics. Okay, so additional thoughts can be any links to the topological states, because there are topological systems that actually exhibit this chiral phonon behavior. And also because 214 system is a superconductivity, and as everybody knows, phonon is an essential part of this superconductivity, and also magnetism is also a part. We can might think some correlation between this superconductivity and also this phonon behavior. With that, I thank you for your attention.
Strontium ruthenate films, single films, have a magnetic anisotropy pointing out of the plane, so, and it's temperature dependent. Are you saying that this is changing for thinner films or for for the heterostructures that your magnetic anisotropy puts your moment exactly in the plane?
Yes, very good question, and I'm sorry that I didn't explain it fully. So this picture should be actually a conical structure. As you said, Schoenstein-Rusen, it has the out of plane as the easy axis, magnetic easy axis, and you have a bunch of portions of magnetism along the out of plane. What I'm showing today here is only in-plane data. So all the data are in plane, and along the out of plane, you don't see this oscillation. Yeah, they are almost the same, actually. So only the in-plane, so again, in-plane is smaller than the out of plane direction, and there you see this type of oscillation.
Thanks.
Thank you.
Is this something you want to comment more about? Or?
Viscosity split?
Yeah. You listed the effects of higher phonons, and on that list you mentioned about this homogeneously viscous split in wave sensitivity. But if it's not your field. So
Yeah, I'm not sure about that. So yeah, I'm sorry. Yeah.
Okay, so we go to the next talk.
Thank you.